Good afternoon. I'm Spot On Weather meteorologist Matthew Euler, and welcome to How the Weather Works training video. This is video number 10 of the How the Weather Works training series. Certainly hope everyone's doing well out there today as we embark on another journey to learn how the weather works. On this particular title slide, I'm showing an example of a special type of weather system that's known as an Alberta Clipper. Now with an Alberta Clipper, and I'll get more into this here in the training, it is a system that generally tends to form on the lee side of the Canadian Rockies in the Alberta province of Canada, and then the upper level winds, the jet stream just kind of moves it along from the northern plains on down into the Midwestern U.S., and right into the eastern seaboard before it moves offshore. And anywhere north of this little Alberta Clipper is where you typically get the bulk of snow in wintertime. These are typically wintertime systems, these Alberta Clippers. And generally, why do we call it a Clipper? Because the upper level winds push this surface low, this little surface pressure system, along fairly quickly. And this is just one example. There's a wide variety of topics today that I'm going to cover with you. And so looking forward to the training, and so let's get right into it. The first thing I want to start today's training off with is the general movement of the synoptic scale features. Generally, the polar front jet stream is going to be that steering mechanism for the synoptic scale features, whether they be lows or high pressure systems. Cutoff lows in general, those are those upper level lows at 500 millibars. In the middle level is the atmosphere that I kind of talked about in the last training video. Those cutoff lows generally have lifted out into a long wave pattern. They'll become embedded within that long wave pattern over time and travel with that long wave pattern. The speed and undulations of long waves, short waves, talked about both of those already. We also talked about jet streaks with attendant regions of positive vorticity advection at PVA and negative vorticity advection NVA. That enables a forecast for both height falls and rises in the upper levels of the atmosphere. Here are a couple graphics I'm showing at the bottom of this slide. The first one, the first pair here on the left, indicates that long wave pattern. These are solid height contour lines. These solid lines are the height contours. The dashed lines indicate shortwave troughs. We have a shortwave ridge over the central U.S. Up into central Canada and Hudson Bay. We have these little shortwave disturbances that propagate through this long wave pattern. The polar front jet stream is that steering mechanism to guide these little disturbances. And ahead of these disturbances, remember from the last training video, I talked about areas of positive vorticity advection, which, by the way, in this particular chart are indicated in this red shading here. We have areas of positive vorticity advection. We have areas of negative vorticity advection. The main points, again, with positive vorticity advection, out ahead of shortwave troughs, we have upper level divergence, height falls, and upward vertical motion rising air from the surface, which results in clouds and stormy weather. Whereas there are certain areas behind, for example, shortwave trough axes, ahead of the shortwave ridges that have negative vorticity advection associated with upper level convergence and sinking air motion and nice weather. So these waves get pushed along, these short waves get pushed along through the long wave pattern. The polar front jet stream is pushing them right on through from west to east in the mid-latitudes. If you look at the far bottom right-hand graphic here, showing the favorable areas of a jet streak. This purplish blue color, generally in the center here, indicates the highest wind speeds associated with the jet streak. And if we divided the jet streak in half, again, remember, the upper left and the right rear quadrants of the jet streak are associated with upper level divergence and rising air motion, removal of mass aloft, while the right front and the left rear quadrants of the jet streak are associated with sinking vertical air motion and upper level convergence, more fair weather. So coupled with the steering effect of the jet stream, this will assist in the prediction of how these pressure systems are going to move over time. Upper level low pressure systems, for example, they tend to travel towards regions of the strongest positive vorticity advection, while surface lows, low pressure, tends to travel towards the regions of the strongest warm air advection. Low pressure systems tend to accelerate and move northeasterly as they strengthen over time. And after occlusion, the center of surface low pressure systems travel with the upper air trough and the fronts begin to dissipate. The air mass contrast decreases across all of the frontal boundaries. Blocking ridges will impede the progress of low pressure systems to the west of the ridge, resulting in a stalling effect and possible retrograde motions. When we talk about that retrograde motion, I mentioned it in a previous How the Weather Works training video. Retrograde refers to pressure systems actually moving backward against the normal flow, backwards towards the west in the mid-latitudes, instead of towards the east. Normally, everything moves from west to east, being pushed along by the jet stream in the mid-latitudes. However, there are cases where we get these large blocking high-latitude ridges, which are going to act as a roadblock. They're going to impede the progress of these surface low-pressure features to the west of that ridge. And that could possibly result in a retrograde motions or even stalling out in a particular area. Let's now turn our attention to another topic today, and it's called the Norwegian cyclone model. And basically, this Norwegian cyclone model shows how upper air and surface events interact to produce cyclogenesis. And we really covered this extensively in my last video. Highly recommend, if you have not already done so, to watch How the Weather Works video number 9, part 9, which I did just recently. I really delve deeper into that connection between surface pressure systems and how they stack up with height in the atmosphere and the upper air features that support them. Now, this Norwegian cyclone model assumes that the upper flow must be conducive to developing cyclone at the surface. Upper features can cause cyclogenesis without any prior development at the surface. I did talk about that in previous videos as well, mainly with the relation of a shortwave trough at 500 millibars, for example. Out ahead of that trough axis is a very favorable area to kick off surface cyclone development as upper level divergence moves over a weak low level frontal zone with a weak thermal contrast across the frontal boundary. That's a prime area, how the upper level, that's a prime example of how those upper level wave features kick off cyclogenesis at the surface. Now, once you get extremely strong thermal or temperature advection, that's going to result from surface cyclonic shear, that increased curvature, cyclonic curvature, the wind field. That can produce enough baroclinicity to cause changes to the jet stream aloft and create waves in the upper flow. Now, the Norwegian cyclone model generally works best when we're dealing with flatter terrain. Mountains, foothills, elevated coastlines, and upslope terrain are going to modify the model. Okay, so when we look at the unimpeded progress of cyclonic curvature, the winds turning in towards low pressure at the surface, we really look at the model as flat terrain, using flat terrain, because mountains, elevated areas are going to definitely modify the airflow. Mountain ranges actually can produce a condition that's known as damming of air masses and serve as physical barriers. They serve as those physical barriers to the motion of surface fronts and surface pressure systems. Terrain can alter circulation patterns as well by channeling the flow. For example, in a valley between mountains, we can get terrain features kind of causing a funneling effect, preventing flow or causing even mechanical lifting. The bottom right-hand portion of this slide, I'm showing you the various stages of development of the wave cyclone using the Norwegian model, generally showing you how the stages progress from stage 1 to stage 4, and the solid black lines indicate those lines of equal barometric pressure known as isobars. You'll notice how we only start off with one closed isobar as the cyclonic cyclonic curvature, that wind flow around this low pressure counterclockwise in the northern hemisphere, begins right at this stage, phase 1, where we have one enclosed isobar around the surface low. But as time moves on, by phase 3, for example, in the Norwegian model, we have a much more tightly wrapped system where these isobars are much closer spaced to each other. And that indicates a lot of wind energy. That indicates a surface low pressure system that is intensifying. And then finally, you get to the occluded stage at phase 4 in the Norwegian cyclone model. And again, you have a very tightly wound up system at this point. And this is a general outline of what the systems would look like in the upper levels, by the way, how things progress in the upper levels here at the bottom. Moving on now to the difference between barotropic and baroclinic instability. This is a very important topic in meteorology, and I wanted to touch on this once more. Generally, baroclinicity is defined as an atmosphere where those isotherms and the isoheights, those height contours, cross each other. So there's a perpendicular component to these two lines, the isotherms and the isoheights or height contours. Barotropic atmosphere, on the other hand, displays we have a parallel isotherm relationship to the isoheights or height contours. So what does this mean? Baroclinic zones are areas where thermal or temperature advection and thermal winds affect the existing flow pattern. Strong thermal advection can actually produce strong thermal winds, and that will alter the jet stream location and can create upper level waves which spur cyclogenesis. So big difference again between barotropic and baroclinic. Barotropic, the isotherms and height contours are parallel to each other on upper level weather charts. Baroclinic, we have crossing or a perpendicular relationship between those isotherms, lines of equal temperature, and the upper level height contours or isoheights. Barotropic, you're generally not going to have any type of temperature advection. With baroclinic, you're going to have temperature advection. Typically, we see barotropic systems. Some examples that I gave in a previous training video, cold core upper level lows become barotropic. Those low pressure systems in the upper levels were initially baroclinic and had a lot of vorticity advection associated with them, as well as temperature contrast and movement of various air masses at the surface associated with baroclinic situations. Another example of a barotropic system would be a warm core low pressure system, such as a tropical cyclone. The barotropic systems, they don't derive their energy necessarily from air mass contrast. Baroclinic systems do. So for example, a warm core low, a tropical cyclone, is not really relying on air mass contrast to intensify. It's relying on underlying heat and moisture picked up from a warmer ocean surface. So just wanted to point out the key differences between these two terms in meteorology. Baroclinic is going to be associated with frontal boundaries. Barotropic, the air mass contrast will be destroyed, as in the case of a cold core upper low, or there will be no fronts at all with a warm core low, the tropical cyclone. Now, during the wintertime in the mid-latitudes especially, we have a large temperature contrast between land and water. So during the winter, the ocean is going to serve as a source region. It's going to be warmer. It's going to be moister. For example, if I bring a cold continental polar air mass out over the Gulf Stream off the U.S. East Coast in wintertime, I'm going to have a large vertical temperature gradient or temperature difference between that surface right there at the Gulf Stream. The Gulf Stream is a very warm ocean current, and aloft, where that cold continental polar air mass is moving over that Gulf Stream. We have an extreme unstable situation in that case, with colder, drier air moving over that warmer Gulf Stream surface. This generally is going to produce an excellent area for storm development and cyclogenesis. This is known as a baroclinic zone, with a thermal wind toward the colder air deflected by Coriolis and becoming a jet streak parallel to the isotherms, those lines of equal temperature. So baroclinic zones, what we're looking for here is large thermal or temperature contrasts. Those are the zones at which areas of low pressure and cyclogenesis occur. Now, baroclinic zones are not confined simply to the ocean basin over warm ocean currents in the winter with cold air moving over them. Baroclinic zones are also very frequent over the middle latitudes during the winter season when we have large temperature contrast, a clash of air masses, extremely cold air, polar air, Arctic air coming down from Canada, meeting warmer, moist, maritime tropical air from the Gulf of Mexico. So the central U.S. is another very good area, flat terrain, where we get good baroclinic zone. If the flow crosses isotherms, by the way, lines of equal temperature, the result will be low-level thermal advection. That is that baroclinic term I described in the previous slide. And if you get a wave to develop beneath the right entry or left exit region of the jet streak, another way to say this is the left front and the right rear quadrants of that jet streak, upper level divergence will occur in those quadrants, and that's going to further remove mass aloft and favor the development of low pressure at the surface or intensify the existing low pressure area. Here are some great examples of baroclinic zones in the middle latitudes. This case on the left is in the wintertime. These dashed blue lines represent thickness values. So we got some extremely cold air pouring in from the upper Midwest, northern plain states, down into the Missouri Valley, down into Oklahoma, Arkansas. Meanwhile, we have warm air that is streaming up ahead of that very cold air that's coming down from Canada. And along this boundary, that very sharp thermal contrast between air masses, the very cold air north of the frontal boundary and the very warm air over the Gulf of Mexico, we have a situation where we have a stationary frontal boundary here. And this is a prime area for surface cyclogenesis to occur. There's a lot of potential energy along this boundary due to this very distinct, very sharp, and very steep thermal gradient. If I were to look at a satellite image for that area, the overall pattern in the clouds indicate where a baroclinic zone is located. Typically what I'm looking for is an S, like an S-shaped pattern to the clouds. You notice how elongated these clouds are? This is indicative of a baroclinic zone. More of an S-shaped pattern with cold air to the north and warm air to the south. In this case on the left, you see there's a lot of wintry precipitation. It's very cold air, it's dense, it's close to this, it remains close to the surface. Precip is falling into this sub-freezing air at the surface, resulting in either ice or a mix of ice, of rain and snow here over parts of Texas on this particular day into the deep south, central Mississippi, and northwestern Alabama. This is a great indicator of baroclinic zones, whether I'm looking at a thickness chart or whether I am looking at a satellite image. All right, now getting back to the topic that I initially started with here today in the training, Alberta Clippers. This is a specific type of shortwave that originates in southwestern Canada in the province of Alberta, hence the name Alberta. The shortwave progresses rapidly in 500 millibar flow in the mid-levels of the atmosphere, and that's going to bring cold, dry air, CP air from that source region in Canada, dumping that colder air into the United States. In summertime, such passages bring temporary relief from heat waves when we get this continental polar air to move down from Canada. But in winter, CP air moving southeastward from the Alberta province of Canada tends to bring clouds and snow to the Great Lakes region, generally associated with these Alberta Clippers. So Alberta, because the system forms on the lee side of the Canadian Rockies, and if you look at the bottom right-hand diagram here, this has to do with conservation of momentum. Generally, as wind flows up the windward side of a mountain range, generally an air column is going to shrink in the vertical. It's going to be a smaller radius. It's going to spin quicker when we have a smaller radius. Okay? So it's a much taller column as it approaches the mountain. But as it goes up the mountain slope to the top of the mountain, the column becomes wider and shorter, which results in greater stability towards the top of the mountain. Now, as air comes down the leeward side of the mountain, that air column stretches out once more, where we have a smaller curvature radius, which results in a much quicker spinning motion. And a lot of people will use the reference of an ice skater. An ice skater brings their arms out away from the body. It's synonymous to this shorter, wider air column. The spin, the vorticity is not going to be as great, so you have greater stability. But as that ice skater brings his or her arms inward towards the body, closer to the body, and shortens that turning radius, the air column becomes more unstable as the vorticity increases, the spinning rate increases. So this is generally the way these Alberta Clippers form. Generally, we get the wind to blow up and over the Canadian Rockies. The air column will shorten and become wider, less spinning at the top of the mountain range, but as the air sinks down the lee side, we get what's known as lee side cyclogenesis, the lee side of a mountain, and we get greater vorticity, positive vorticity, greater spinning as this curvature radius decreases. Here's an example of the elevation ranges in the Alberta province of Canada. Generally showing the maroons and the reds here are the higher elevations. And Calgary is located in Alberta. It's a city in Canada located in the Alberta province. It's generally the lee side of the Canadian Rockies here. And so this is where your air would sink, the air column would get taller, and the curvature radius would also get smaller or decrease, causing a spin up of low pressure in the vicinity of Calgary. And then that system is going to follow these general tracks. If you look at the dark lines here in the upper right-hand corner, showing you the general tracks of these Alberta Clippers. This is from 1986 to 2000. This is a general track from Alberta, Canada province here on into the upper Midwest. Another effect that I wanted to talk about and touch on in today's training is the cold air damming effect. Now, what happens with the cold air damming effect is the Appalachian Mountains are the main mountain range that we talk about. We're mainly talking about the eastern United States, between the Appalachian Mountains to the East Coast. The Appalachian Mountains, or any other mountain chain for that example, the Rockies can do this as well, by the way. They can dam the flow of air and impede the progress of surface fronts and these surface pressure systems. For the Appalachian case over the eastern U.S., where you see cold air damming quite frequently during the cold season, when high pressure systems move offshore of New England, their clockwise flow around these highs produces a cold northeasterly wind into coastal regions east of the Appalachian Mountains. Now, the mountains, what they do, since the air is so cold and dense, it wants to be right close to the surface. So as the colder, denser air moves towards the east side of the Appalachian Mountains, it doesn't want to, let's just say, it remains trapped in the low levels of the atmosphere. So let me go ahead and show you here. I'll keep going on with this. The wedge of cold air is strong enough to retard the motion of approaching warm fronts, by the way, as well, causing them to kink. The Appalachians also divert lows attempting to move north from the Gulf of Mexico and southeastern U.S. to the east or to the west of the mountains. So the Appalachians play a significant role in the weather along the East Coast. If the steering forces in the upper atmosphere force a low from the south over the higher terrain, the low will be physically lifted and weakened. Lows traveling from west to east will also experience increasing friction over the mountains, with lee side cyclogenesis possibly strengthening. So now let's take a look at cold air damming in general. All right, let's see here. All right, so what we have going on, we have in the low levels of the atmosphere, we have this cold, dense air. Usually it's less than 32 degrees Fahrenheit in winter. And the cold, dense air, this mountain range, we'll just call this the Appalachian Mountains. That cold, dense air is trying to move up and over the mountain slope and spill down this other side of it. But because the air is so cold and dense, it just simply can't get there. It can't go all the way up this mountain slope. It's too heavy. So what you have for days on end is this cold, dense air, this cold air damming in place east of the Appalachian Mountains. And what's causing it is the flow of air around a high pressure system to the north, just off the coast of New England. And let me go ahead and draw this out for you. Okay, so we have high pressure, and generally the flow around high pressure is going to be clockwise in the northern hemisphere. And so what happens is you get this wind flow, colder, denser air on the front side of this anticyclone over New England. As it moves offshore, this persistent northeasterly wind flow and the cold, dense air just kind of banks up against the Appalachian Mountains. Now, what you can have happen sometimes is you get some of this warmer air from the southwest. Warm air it's less dense, so it's going to move up and over the cooler air, the colder air at the surface. And what you might get sometimes is rain that's falling from the base of the cloud into this cold, dense air east of the Appalachian Mountains. And it may actually result in freezing type of precipitation, such as freezing rain. And that is quite common too during the winter season. So cold air damming is definitely something that is very predominant during the winter. When we get cold core anticyclones over New England, pushing offshore the New England coast. And a lot of times during the winter, what happens is as this air moves up against the mountains, this area remains socked in low clouds too for long periods of time when you have cold air damming. Additional things we want to talk about today are different types of low pressure systems. We're going to talk about track of the East Texas Hatteras Low. The polar front jet stream generally moves southward to the Gulf Coast with a jet streak over Texas in this case. So these East Texas Hatteras Lows, they're going to form in the mid-latitudes during the winter season. So you got a very deeply digging polar front jet stream all the way to the Gulf Coast with a jet streak over Texas. Upper level divergence and vorticity are going to favor the development of low pressure, cyclogenesis. At the surface, usually you have a stationary frontal boundary that's situated along the Gulf Coast between high pressure, where you have cold continental polar air to the north of the frontal boundary, and high pressure with warm maritime tropical air over the Gulf of Mexico. So we have that thermal contrast between one side of the front to the other. So we have baroclinicity, which is reinforced by very copious amounts of moisture in the Gulf, from the Gulf of Mexico coming in. The storm's going to develop, and then it's going to intensify as it moves towards the east-northeast through Georgia, reaching the mature stage. Sometimes these East Texas Hatteras Lows will stay offshore of Georgia and proceed just up off the mid-Atlantic coast during the winter season too. The occlusion begins as the storm tracks to the northeast through the Carolinas, and the storm draws moisture in from the cool waters of the Atlantic. So moisture usually gets pulled in north of the low pressure track, the storm track, and so you get a lot of moisture. A lot of cases across southeastern Virginia and into parts of the mid-Atlantic on the coast, you get a lot of times you get cold rain in the winter season with these tracks. And further inland, you get snow. And pretty good snow at that. The rain-snow line usually sets up into central Virginia. Any points west of central Virginia are pretty much all snow. Any points east of central Virginia towards the coast is usually a cold rain. Now, if the storm is far enough east of the coast or remains offshore, you can get cyclogenesis at that triple point, which could produce a Hatteras Low near Cape Hatteras. So things can easily transfer as far as energy from the East Texas Low all to a Hatteras type low. Otherwise, this influx of moisture produces heavy snowfall in advance of the warm front and in the wraparound portion of the storm where temps remain cold enough. That is your I-95 type storms in the winter season. Richmond, Virginia, up to Washington, D.C., parts of western North Carolina as well, especially as you get towards the mountains, towards Asheville. That is a prime example of a case where you get some heavy snowfall with a Hatteras type low. And I talked a little bit about this before. Let me go back to my main pointer here, but generally you get a negatively tilted trough. And remember, with a negatively tilted trough, That trough axis, the dashed line here, extends from northwest to southeast. This negative tilt toward cold air with height favors a wraparound effect and a very intense cyclone at the surface. It draws moisture into the cool regions of the cyclone is what it does. Here's an example of a Cape Hatteras Low, a nor'easter. Initially, you might have an East Texas low forming over the western Gulf of Mexico, moving either on this track over the through Georgia, through western North Carolina, up along the spine of the Appalachians. In other cases, you get this Gulf low or this East Texas low to generally move out over northern Florida and then right off the southeastern coast. And then sometimes energy will transfer to a what's known as a Hatteras Low, just off of Cape Hatteras, North Carolina, and that's going to generally move out towards the North Atlantic. Sometimes these Hatteras lows can result in very intense nor'easters all the way up to Maine. So if that low pressure track is further to the west, closer to the New England coast, areas along New England could really get heavy snowfalls in this situation. Additionally, there's some other low pressure systems on this particular graphic as well. The Colorado low and its track for the Midwest on up in eastern Canada. You have a Gulf of Alaska low, generally moving towards western Canada, Vancouver area, and then Alberta Clipper, as I already discussed. Right, so I'm going to end today's training on severe weather forecasting. Some of the main thoughts about severe weather forecasting, what to look for. Continental polar air mass is generally going to move south out of Canada during the wintertime, and then you're going to have a maritime tropical air mass moving north from the Gulf of Mexico. Eventually, these air masses are going to meet. That air mass contrast along a frontal boundary is going to serve as potential energy. If we look at 300 millibars at 30,000 feet above the ground, there's a vigorous jet stream or jet streak which exists. In this bottom right-hand graphic, I'm showing this lighter magenta color. That indicates the strongest winds within the jet core, or the jet axis. And generally those are located just off the coast of Florida on out to the western Atlantic in this case. So at the surface, you're going to look for the area of severe weather to occur where the jet streaks provide that excessive mass removal aloft, divergence aloft in the form of speed divergence. Pay attention to the location of these jet streaks here at the bottom right in this graphic. Remember, if your location is beneath that right entry or left exit regions of a jet streak, or the left front and right rear quadrants, look for cyclogenesis and severe weather to occur nearest the surface low. That's where the most energy is going to be occurring. 2, we want to look for strong thermal or temperature contrast parallel to a frontal boundary. We're looking for those packed isotherms lines of equal temperature at 700 millibars or 10,000 feet. 3, we want to watch for the speed of the front and orientation of upper level winds in relation to the surface front. Severe weather is most likely with rapidly moving surface fronts, as the 700 millibar iso heights, or those height contours, run more perpendicular to surface fronts. So here's an example. Let me go ahead and draw this out for you. So let's say that we have a surface cold front. Okay, it's moving from west to east, so it's generally moving this direction. Okay, and then let's say these are, I'm going to show you 2 examples here. This is an example of the height contours at 500 millibars, and they are orientated perpendicular to the surface front. So that means my winds are going to be blowing perpendicular to this surface front, which is going to result in a faster moving cold front. Whenever you have colder, denser air undercutting warmer, moist air ahead of a cold front, and it's moving at an accelerated rate of speed, that's going to tend to result in more vigorous upward vertical motion. Okay, so you want to watch out for that. A lot of energy is going to be utilized in pushing this front along at a quick rate. It's going to result in more vigorous rising air motion in the warm sector ahead of the cold front. Let me show you one other case here. Go ahead and route out this. Okay, I'll do this. I'll do my eraser. Okay, let me do an example of a slow-moving cold front now. Just a slow-moving front in general. So we have a cold front, same thing. And now these solid red lines are going to indicate my height contours. Notice how these height contours are now orientated parallel. They're parallel to the surface front. In this case, we're going to get a slow-moving front. And we won't have as great of a chance or probability of severe weather when we have mid and upper level winds parallel to the surface front. All right. So I just wanted to point that out. All right, let's keep moving along in the training. 4 says a dry line will separate moist, empty air from the Gulf of Mexico and drier continental tropical air from the southwestern U.S. A dry line occurs a couple hundred miles ahead of the surface cold front. So in this case now, with a dry line, we have a surface front coming in. Most of the time this is going to be into Texas. And then I'll draw this dash line out. This is the dry line itself ahead of the surface cold front. Okay. So what happens is we have warm, moist, maritime tropical air that is coming up from the Gulf of Mexico. The Gulf of Mexico will be down in this location here in this example. So I have warm, moist, maritime tropical air converging with drier continental tropical air. Hot and dry continental tropical air. And what this creates is a very drastic moisture gradient. Very muggy. We may have dew points in the 70s ahead of the dry line. Behind the dry line, we're going to have dew points maybe in the 50s. So we may have a 20-degree Fahrenheit dew point difference from ahead of the dry line to behind the dry line. And that density difference, the moisture difference, is going to result moist air being less dense, dry air being more dense. It's going to cause a significant area of thunderstorms to just explode right along the boundary of the dry line out ahead of it. And these type of storms over Texas typically are associated with very large hail as the dry line moves in with that major moisture gradient, major moisture difference across the dry line itself. Okay. Moving on now. Number 5 for severe weather forecasting. I'm looking for strong upper air divergence at 500 millibars and above that level too, which is going to favor development of a chimney effect. Upper level divergence aloft and low level convergence at the surface. Those are the 2 things I'm looking for. I want upward vertical rising air motion to get my severe weather. 6, extensive low-level warm air advection. That's going to occur well in advance of the cold front from 850 millibars at about 5,000 feet, right on down to the surface. This level contains the bulk of moisture, by the way, surface to 850 millibars. So we have warm and moist air that's flowing out ahead in advance of the cold front. Now let me draw this out here. This is the cold front. Sometimes what we get to have, what happens ahead of these cold fronts is something known as a low-level jet. And these low-level jets generally tend to blow in the warm sector ahead of cold fronts, and they can be very intense. Low-level jets are going to transport warmth and moisture at a very accelerated rate ahead of the surface cold front. And this is going to add to the instability of the air mass ahead of the cold front. Just want to draw that out. All right, let's keep moving on here. Number 7, trapping inversions at 850 millibars to 800 millibars exist above warm, moist regions. Also look at mid-level dry air intrusion. We get dry pockets of air in the mid-levels, warm, moist air beneath it. So we have to look at all these factors. Additionally, increased cyclonic vorticity if you have an area of PVA or positive vorticity advection. Of course, the higher the value of the PVA, the higher that vorticity value, the more accelerated the upward vertical motion will be, that rising air motion. All right, that wraps up the training today. We're in part 10 of How the Weather Works training series. Let me go ahead and go back to my laser pointer. Okay, so in today's training, what we looked at a variety of topics. We started off with a discussion on the movement of synoptic scale features in the mid-latitudes, between 30 and 60 degrees latitude, by the way. That's the mid-latitudes. We talked about how the polar front jet stream pushes these synoptic scale features along and moves them from west to east. The speed and undulations, the waviness of long waves, short waves, jet streaks with attendant regions of PVA and MVA. That will enable a forecast for height rises and falls in the upper atmosphere over a specific station. Additionally, we talked about the movement of upper-level low-pressure systems. They tend to travel towards regions of strongest PVA, positive vorticity advection, while surface low-pressure systems tend to travel towards the regions of strongest warm air advection. And oh, by the way, those surface low-pressure systems also travel towards the greatest pressure falls. You would look typically at an isobaric gradient, lines of pressure change to see where the greatest pressure falls are occurring. That is where your surface low pressure is going to travel towards. Low pressure systems, they tend to accelerate. They move northeasterly in the northern hemisphere as they get stronger. We talked about blocking ridges, which impede the progress of low pressure systems to the west of the ridge. Sometimes that results in a stalling weather pattern and possible retrograde motions. The Norwegian cyclone model went a little bit into detail on that, working best over flatter terrain, away from the modifying effects of mountains, foothills, elevated coastlines. Mountain ranges can also produce a damming of air masses and serve as physical barriers to the motions of fronts and systems. Barotropic versus baroclinic instability. Barotropic, again, is going to be an atmosphere which displays no temperature advection. You're going to have no thickness advection either. You're going to have parallel isotherms to isoheights. Baroclinic, on the other hand, refers to an atmosphere where we have advection of some meteorological property where isotherms and isoheights cross each other. There's a perpendicular component. Baroclinic zones, a very important area to look for the development of low pressure systems. Talked about the favorable locations of baroclinic zones. These zones have sharp thermal contrasts from one side to the other. And then I showed an example here on the left of what it would look like on a 1,000 to 500 millibar thickness chart where we have very cold air being separated by this stationary frontal boundary, cold air to the north, warm air to the south. The wave of low pressure is generally going to develop in this zone. And that's also going to result in an acceleration of the jet streak, by the way. The jet stream is typically going to be located right above the tightest 1,000 to 500 millibar thickness packing. So it's a good probability you're going to have upper level divergence associated with a jet streak in this general area as well. Alberta Clippers, a special type of shortwave or surface low pressure system, generally showing you, we talked about how these systems develop, how the air column will fluctuate from tall with a smaller radius curvature to wider and a much basically wide and shorter column, and then become again much taller on the lee side of the mountainous area, causing the spinning rate to increase, the vorticity to increase on the lee side of the mountain. That's lee side cyclogenesis. And by the way, this not only happens in the Alberta province east of the Canadian Rockies, but it also happens in eastern Colorado with the Colorado Low. Cold air damming effect, when cold air gets trapped east of a mountain range. This can also happen out in eastern Colorado when you get a northeasterly and easterly wind associated with a continental polar air mass where you have high pressure to the north over Montana. But I really focused the discussion on the cold air damming effect east of the Appalachian Mountains. Generally a very strong cold air mass, a strong anticyclone off the coast of New England with clockwise flow, northeasterly winds. Cold, dense air at the surface gets trapped on the east side of the Appalachian Mountains. And it usually results in a period of low stratus clouds from the east side of the Appalachian Mountains all the way to the coastline. I've seen it here in eastern Virginia quite a bit in the wintertime. We get a low-level northeasterly wind flow, a maritime polar air mass banking up against continental polar and maritime polar air masses, kind of banking up against the eastern side of the Appalachian Mountains. Here is a diagram explaining the effect. Sometimes you get a situation where a warmer air is going to ride up and over the colder, denser air associated with cold air damming, and the precip is going to start out as liquid in the warmer elevated layer, but then as it falls through this sub-freezing layer, this cold, dense layer at the surface, it can result in a variety of precipitation types in the winter season. A snow-rain mix, you can get some icing effects as well with freezing rain. It just depends on the vertical extent of the elevated melting layer aloft, temperature area greater than 32 degrees, as well as how thick that cold dense layer is at the surface. Talked about East Texas and Hatteras Lows in the wintertime. You get the polar front jet stream to really dive deep to the south, into the deep south, a stationary boundary located along the Gulf Coast. And these were the different tracks associated with the East Texas Low or the Gulf Low, and then the Hatteras Low. Very common area for extratropical cyclone development, especially in the winter season, as there's a large contrast between the cold continental polar air over this landmass behind that low and the warmer, milder air over the Gulf Stream current. So this is a great baroclinic zone between warm, moist air over the Gulf Stream and much colder, drier air over the land, eastern U.S. land areas in the wintertime. This also happens in the western Pacific, by the way, off the coast of Siberia. Some forecasting tips for severe weather. Generally what we're looking for is a vigorous jet streak, which we're showing in the bottom right-hand graphic here, the magenta and purple shading. The lightest magenta colors indicate the strongest winds. This is due to speed divergence, where removal of mass aloft. If you're in the left front or right rear quadrants of the jet streak, that's a favorable area for upward vertical motion, rising air, and cyclogenesis. The strongest or most severe weather, by the way, again, is nearest the surface low. Also, you look for strong temperature contrast parallel to a frontal boundary. If you're looking at packed isotherms at 700 millibars, you also want to watch for the speed of the front and orientation of the upper level winds. Are they perpendicular? Are they parallel? A dry line, talked about that. It's a special boundary separating very moist air, warm moist air, from very dry air. So really it's a moisture discontinuity boundary that can really kick off severe thunderstorms, especially over North Texas. These are associated with some extremely large hail sizes. Additionally, we look for the chimney effect up at 500 millibars at 18,000 feet, low-level convergence. We have exhaust aloft at upper-level divergence, removal of mass. We also want to look at the low-level warm air advection to see if it's occurring in advance of a cold front from about 850 millibars to the surface. And a very quickly moving transport of warmth and moisture occurs in association with what's known as a low-level jet stream, typically around 850 millibars. Trapping inversions at 850 to 800 millibars exist above the moist, warm, moist regions. If you get that lid or trapping inversion to break, then you can get explosive upward vertical motion. And then increased cyclonic vorticity and PVA is forecast. That's another thing you really want to be paying attention to for severe weather and cyclogenesis. All right, everybody. Thank you so much for watching today's training video on how the weather works. This was part 10. We covered a wide variety of topics, more mid-latitude focused once again. So thank you so much for subscribing to the Spot on Weather YouTube channel. Again, I hope everybody is learning a great deal out there. And I do wish everybody a very good, happy, fun Memorial Day weekend. Don't forget to remember those who paid the ultimate sacrifice for our country, who basically gave it all so we can enjoy things we enjoy today here in this country. So, all right. Thank you very much. And until next time, take care and God bless. Feel free to drop me a comment on these videos on YouTube. Still a lot more training to come. Looking forward to it as we progress through the summer and hurricane season together. Take care, everybody, and God bless.